one can distinguish between different kind of correlations. One you might have heard already, that's static and dynamic correlation. But they're sort of more, and I mean they sort of highlight different aspects of the whole problem. The basic problem is, I mean, electrons have the same charge, though they repel each other. And that effect, that interaction should be represented. And this Hartree-Fock it's a mean field, but you also can call it an independent particle model. Because one electron moves around independently where at this time all the other electrons are. They sort of just see the average effect that they are electrons, meaning essentially that the attraction by the nucleus is reduced. And you can see that if you remove that mean field potential of all the other electrons, and you would do a calculation with that, you get orbitals which are much more compact, much smaller, because then the electrons feel, or the electron feels the full nuclear charge, whereas they are sort of, normally they are screened by the other electrons. And all the ones who had chemical S, you might remember that we talked about a screening of the nuclear charge at some time, and there's sort of a bit of an old-fashioned way of trying to incorporate that. But now with real Hartree-Fock theory, I mean, solving the Hartree-Fock equations and getting this Hartree-Fock potential does that, essentially. But we can distinguish between intra-orbital and inter-orbital correlation. I mean, the intra-orbital is, you have, in a closed shell system, you have two electrons sitting in the same orbital, 2a minus, two electrons in an orbital. But because of the Pauli principle, they have opposite spin. Opposite spin. Whereas if you have them in different orbitals, then you can still have the situation with opposite spins, but you can also have the situation with parallel spins. Which one do you think is the larger effect? Yeah?
It's one on the right, because there are more pairs than there's in...
Yes, that's true. There are more pairs here. So you have this more often. I mean, you have this as many times as you have an orbital, and you have that as many times as you have pairs of orbitals. But if you look at one of them, which one is the larger effect? Yes?
Well, obviously, the other one.
The other one. Because if they sit in the same orbital, they are much closer to each other than if they sit in different orbitals. So the individual one, this is the larger effect, but in total, because you have many more of those, this is in total a larger effect. Then one talks about Coulomb versus Fermi. I mean, that you probably don't see a lot in the literature, but you might see Coulomb versus Fermi correlation. And Coulomb is if they have opposite spin. Opposite spin. And Fermi is then obviously if they have same spin. So if I compare that with up here, here we have intra and intercorrelation, interorbital correlation, because we have this with opposite spin and I have that with opposite spin. Whereas that one we only have for the interorbital. correlation. And this Fermi correlation is, of course, a consequence of the Pauli principle. Because you can't have two electrons with parallel spin in the same orbital. So that correlation is in a way included in our anti-symmetric wave function, where we sort of have the Pauli exclusion principle. So that part is actually, to a certain part, that is included in Hartree-Fock because you can't have it with the intraorbital. In that context, one talks often about Coulomb and Fermi holes. And if you talk about that, what you're talking about is you're looking at the probability to find one electron in the neighborhood of another electron. So if I, for example, on the axis here, have the distance between two electrons, here's 0. So let's say I have electron 1 is the one I take as the origin, and then I look at what is the probability to find a second electron in the neighborhood of the first electron. So I have here sort of a probability. And then, obviously, at the point where the electron is, there should be no probability for finding a second electron. So it sort of should look like something like this. You have, the closer they get to each other, the smaller the probability goes to 0. That's sort of the Coulomb or Fermi hole. And a Hartree-Fock wave function is not going to give you that. Hartree-Fock wave function is going to give you at all something like this. So it's trying to recover that situation which we want to do with, or have to do, with our wave function methods. And the last kind of correlation is maybe the best known phrase. So 3, that's static versus dynamic correlation. Versus dynamic correlation. So we have static versus dynamic correlation, and you could sort of say that static correlation is actually not really correlation. At least not this, what we're talking about here. It still means that it's something which we can't recover with a single determinate wave function. And we're going to look at that a bit more this morning. The problem in static correlation is that you have a near degeneracy between two electron configurations. And therefore the one determinate one configuration wave function is qualitatively a wrong description of your system. And one example is for example this beryllium, where I said the simplest configuration would be this one, 1s doubly occupied, 2s doubly occupied. But there's another configuration, which is 1s doubly occupied, 2s singly, 2p singly, which is very close in energy. So they are not exactly degenerate, but they are as near degeneracy. And then if you look at the many determinate wave function, many configuration wave function, you will see that the weight of those two configurations, there's not much big difference between them. So in this situation, we have near degeneracies, you have a problem that sort of the one determinate wave function is qualitatively not correct. And that's one example. The other example, much more important for us, is when you break bonds. And we're going to look at that a bit later. I want to discuss the hydrogen molecule as a simple example for that. Where this happens when you break the bonds, you get two determinants or two configurations which are very close in energy. And then you just, it doesn't make sense to treat it like this. Whereas the dynamic dynamic correlation, that is all the thing we discussed before, Coulomb and Fermi hole. So, for the static correlation, the remedy is not to take one determinant, but to take all the ones which are relevant, all the ones which are close in energy, all the configurations which are close in energy. So that's you can solve that by including a few other electron configurations. Dynamic electron correlation, unfortunately, you have to include a lot of them. Here you have a few large contributions. Here you have a lot of small